Science lab is for all young kids. Kids who are 6-year-old and also kids who are 90+-year-old. Unfortunately, almost everywhere in the world, science is being taught only from the books, not giving much importance to the experimental part, not giving much importance to understanding the real concept by doing and learning. Maybe this picture can explain the entire situation. If we have a vehicle with two wheels of this nature, it doesn't go anywhere. And this is what is happening in the education system from the place where I come, that is India, and maybe this is true with all other parts of the world. And therefore there is an extreme need for developing open science experiments, for developing open software and hardware framework for doing scientific experiments and introducing them to school children. Now the question is why these experiments are ignored in our education system. Maybe there is a lack of interest, maybe we have too much of examination oriented evaluation system, or lack of affordable equipment. Now all these things, all these questions can be answered by providing very low cost and affordable software hardware frameworks and open science experiments. At Pocket Science Lab, this is in fact our aim to deliver low cost equipment to millions of children everywhere around the world and enable them to do experiments on their own and learn scientific subjects. In the beginning, I'd like to introduce you to the main component of this Pocket Science Lab. We call it ExpEYES. In fact, it was Experiments for Young Engineers and Scientists. EYES was the short form. But again, if you Google EYES, you will get so many other things. So just to make it a little odd, we had added that EXP in the beginning. Basically, it's a small computer interface. Software and hardware both are open source. You have a built-in signal generator. You have a digital storage oscilloscope built in it. It comes with a microsecond time resolution, and basically it is powered by Python programming language. So for people like us who come from basically like science teachers, those who do not have any basic knowledge of computer programming, for them also learning this Python code in a couple of days will be very easy, and they'll have enough knowledge to do experiments with this interface. That's why Python was selected, and Python in fact made our job easy to develop these experiments. Let's not talk more about the features. Basically, I'll just talk about what experiments we have been developing during our Google Summer of Code project. This is the main graphical user interface that comes with the device. It functions as a 4-channel storage oscilloscope, and as you can see, it has all the functions which are available on a very costly digital storage oscilloscope. These were the experiments which were developed in the beginning. Students can do experiments like study of logic gates, basics of electronics. They can do these simple experiments also, like interference of sound. Now if you think of the conventional equipment that is needed to understand this phenomena, you need 2 sources of sound, and to drive them you need 2 function generators, signal generators, which are very costly. Then you need a very good quality sensor to pick up the sound, and then you need a digital storage oscilloscope to fetch the data and plot it in real time. That becomes a very costly affair. And this experiment we study in 11th standard in India. We call it as Foster PUC. Now if you think of having a laboratory which is equipped with digital storage oscilloscopes, function generators, that is quite not affordable in most of the part of India, in rural schools and colleges. But this Pocket Science Lab provides everything that is required for performing such experiments in the laboratory. In fact, a student can afford to have his own laboratory because of this kit. What we have used is two small piezo buzzers, which are very low cost, and there is a small mic. And this can be plugged into any PC or laptop, or even now Android mobile app is available. So that makes it maybe the most affordable pocket science lab in the world. If, for example, studying transistor characteristics, again you need digital storage oscilloscopes, or a simple oscilloscope, you need a function generator, you need power supplies, you need different meters, you need amplifiers. And that's why all these equipments are not at all affordable. Pocket Science Lab can provide a solution to these problems. There is one more unique experiment that can be done with this instrument, measuring acceleration due to gravity by using a concept of time of flight. You can just drop some object from certain height, measure the height, and measure the time for flight of that object, and you can calculate acceleration due to gravity. Now if you want to do this using a conventional setup, again it's very costly. And there are many more experiments which we have already designed for Pocket Science Lab. Recently I had an opportunity to work for my Google Summer of Code project under mentorship of Mr. Mario and Honfok. This is the gallery of sensors and devices which I use for developing new science experiments. And I could do all these things with bare minimum knowledge of Python and little familiarity with ExpEYES. You can see there are various sensors there in the image. I used ultrasonic SRF05 sensor for motion detector. I used accelerometers, simple humidity sensors, temperature sensors. We used a small DC motor as a pickup device. Then we used some gas sensors. And of course it can work with Raspberry Pi also. Our idea was to reduce the total cost of the equipment. Okay, I have listed some sensors which I have used for developing these experiments. I used ADXL 335 accelerometer, magnetic field sensor. This can be used for many other purposes, like if you want to measure rotational speed of a motor, you want to measure rotational speed of anemometer, that sensor can be used. We used infrared object sensors. Then one more innovative device that we used, which was homemade, a photo gate for measuring time intervals of different oscillating systems. We used ATtiny 85 microcontroller for generating sine waves. And this year we had one more objective of producing a very low cost data acquisition system, which can be used as a standalone system for having your, say, a weather station. A small portable weather station which can be powered by small batteries, which can be connected to a Raspberry Pi, and it can tweet the data if network is available from anywhere. We could design our own anemometer, and we are working on designing a device which can give us direction of wind speed. We could measure wind speed, but direction of wind speed, those devices are very costly, but we are trying to have a homemade alternative for it. For measuring atmospheric pressure, we used BMP 180 sensor, and for humidity, we used analog sensors. Okay, these are the experimental setups which we have developed during this project. For studying Newton's laws of motion, many proprietary setups, closed source devices are available from some companies, but they will cost you in millions. We tried to develop one setup using ExpEYES Pocket Science Lab, and we could reduce the cost by almost 95%. The device, which cost about 2.5 lakh rupees in India, okay, now that device is available for 12 to 15,000 rupees. Then we could develop some setup for studying motion graphs. Kids study motion graphs when they come to 6th and 7th standard, like plotting velocity time graph, acceleration time graph, and position time graph in different systems. Studying oscillations is a very interesting phenomena, and if you want to study oscillations, again you need very costly setups. So these are the experiments which we developed. Studying oscillations of coupled pendula is very interesting phenomena. Like you can have two oscillating systems, couple them with a spring or an elastic band, and study those oscillations. Now again, if you want to do it with a conventional setup, very costly equipments are required, sensors are required. what we have used here is, you can see there on that stand, we used a small DC motor as a pickup device. There are two DC motors and pendula are attached to those DC motors. So when pendulum oscillates, DC motor, the wheel of the DC motor moves and electricity is generated. That electricity is very small, voltage generated is very small, so that needs to be amplified. There is an inbuilt amplifier available in this pocket science lab that amplifies it to 50 times, and that can be plotted in real time. You can see that there is a very interesting graph there. This experiment can be done in 3 different modes. You can set those pendulums to oscillate in phase like this. You can set them to oscillate out of phase. You can just keep one pendulum at rest and oscillate the other pendulum. So first pendulum, when it oscillates, its amplitude goes on decreasing and the second pendulum picks up. Amplitude increases. Again, the amplitude of the second pendulum decreases and amplitude of the first pendulum starts increasing. And there is a direct transfer of energy from one pendulum to the other pendulum through that coupled spring. With this kind of equipment, everything is locally available. We have used a small spring that is available and 2 DC motors. And you can see the result. When the pendula are moving in phase, you can see both the waves are in phase. They are plotted together in the third graph. And there is a very simple Python code running behind it. Just 3 or 4 lines. Now Python makes that job easy even for a non-programmer like me, because it has a very powerful library of libraries for scientific calculations like SciPy and NumPy can be used. Same case, now pendula are oscillating out of phase. You can see those individual graphs for 2 systems and here they are plotted together. One can clearly understand what exactly out of phase. When I was in school, or you can say in college, I could never understand what is this concept of phase. We talk about single phase AC, we talk about 2-phase AC, we talk about 3-phase AC. But that is never really shown to the kids. In fact, we are never taught what is the exact difference between AC and DC. You ask any person what is the real difference between AC and DC, the only answer that they will give you is AC is alternating current and DC is direct current. If you ask the kid what exactly happens in that wire when AC flows, if you ask kid what exactly happens in the wire when DC is flowing through it, and you will not get the answer. In fact, I could understand these things when I started teaching physics. I never understood these things when I was actually in my college. So this can give clear idea about what do you mean by waves which are in phase, waves which are out of phase when the pendula are in unison. Okay, here again, when you couple this pendula and data is fetched by a single channel, you get that modulated wave there. You can see for the first pendulum, okay, I was talking about the third phase, keep one pendulum at rest and move the other one, right? Then there will be energy transfer. So you can see that red colored curve. When amplitude of the first curve is maximum, amplitude of the second curve is at the minimum. And then second pendulum will have a maximum amplitude, first will have a minimum amplitude, both are plotted together. This is one example for open experiment. We used ultrasonic position sensor for plotting motion graphs. In the figure on left hand side there you can see there is one pendulum oscillating in front of that sensor. And there is a vehicle. These are the results you can see here in this graph. And there is one here. SRF05 ultrasonic sensor is a very low cost sensor available almost everywhere. In India it's about 150 rupees. We have one such setup in our laboratory made by a foreign company, and that costed us about 1,10,000 rupees, which is huge amount. And we could design this setup in less than 2% of that cost. And anybody can easily do it, just they need to buy one ultrasonic SRF sensor. Another interesting experiment is Lissajous figures. We studied in colleges. There is a very complicated mathematical analysis related to this Lissajous figures. No one really understands how it happens. But here, you can actually show them how Lissajous figures can be plotted. You can combine 2 waves. Maybe you combine 2 orthogonal waves together, then you get the resultant patterns. Engineering students, they do this with the help of CRO. CRO is a cathode ray oscilloscope or a digital oscilloscope. We used a small 80 tiny microcontroller here for generating sine waves, and you can see the result. Just play with the frequencies. Change the frequency of one source, keep the other source frequency constant, go on varying the frequencies, you'll get beautiful patterns, different patterns on the screen. And that data can be fetched in real time with Pocket Science Lab. Okay, just by changing the amplitude and changing the ratio of frequencies, you can get different patterns. I just demonstrated these things to my students with Pocket Science Lab and then just left this kit with them. Next day, my students came with this kind of result. I never thought of creating Lissajous figures using square waves. Generally, we always use sine waves for creating Lissajous figures. So when my students saw that they are able to do it with sine waves, why not try it with square waves? And they could get many beautiful patterns with square waves like this. So that clearly shows, if we give affordable equipment to kids, if we give opportunity to kids to play with the hardware, they can come with wonderful results. In fact, now every small kid is familiar with software part of these kind of applications. Give them a mobile phone, in one day they'll be 100% familiar with all the tools which are there in a mobile phone. But same thing doesn't happen with the hardware part, because we do not allow them to play with the hardware. Maybe Pocket Science Lab is a solution for such things. We did some experiments with accelerometer. ADXL was used. The accelerometer which is there in your mobile phone. So we thought of having the same thing separately, so that it can be used for studying oscillations of any complex system. You can see there is a graph there that is simply generated by shaking that accelerometer. And again, a very simple Python code is working behind it. This year my mentor suggested to add something more in my Google Summer of Code project. He asked me whether can we collect weather related data and just tweet it on a web server. And we just tried to do that. We used a very simple humidity sensor for measuring relative humidity. Those are the plots there. We used LM35 temperature sensor for measuring temperature, and different barometric pressure sensors, homemade anemometer and wind speed measuring device. And again, using Python code, we could create one data logger which has 4 channels. So we can connect 4 different sensors at a time, and data can be recorded continuously, and that can be auto-tweeted. One more interesting concept is studying oscillations in viscous liquids. And that can also be done using this instrument. You can see that that curve shows damping of the spring oscillations. This is what I was talking about. The final result of that weather station is we now have auto-tweeting weather data station, which can be configured to tweet the data automatically, and it can be displayed on any web map. For creating anemometer, I had a unique problem too, which was detect the speed of wind using a very low-cost device. And my students suggested me to use this Hall sensor, magnetic sensor, and that we could use for measuring rotational speed of the motor. For studying collisions of 2 systems, we needed a very low-cost pressure sensor. And we got this idea from the internet itself. Okay, these small piezo buzzers will be there, a very low-cost device that can be used to interface with ExpEYES and can be used for studying different collision experiments. Another example, studying resonance of different containers, resonance of different cavities. And in high school syllabus also, kids study resonance experiments. For studying resonant frequency of cantilever beams, different beams. As we all know, frequency depends on the length of the beam. And that can be very easily demonstrated using a setup like this. What I have used is a small speaker. On that, a plastic glass is mounted, and on that glass you can paste beams of different lengths. You can use bicycle spokes or straws or small sticks. Have 5 to 10 different spokes of different lengths, and the speaker is directly connected to ExpEYES Pocket Science Lab. There is a provision to change the frequency of the source. go on playing with the frequencies, and you'll be able to see that at different frequencies, different length of the beam will start vibrating. That is the easiest experiment that can be used to demonstrate relation between resonant frequency and the length of the system. Pocket Science Lab is now also available on Android phones. There is an Android app available for this. It was in fact an amazing journey to work with my mentors at FOSSASIA, with every day a new critical piece of knowledge to be learned. There were some challenges because I'm not a computer programmer, but Python community is so strong that I used to just post messages, yeah, I want to do this, I have a difficulty in this, and within a couple of hours somebody from somewhere around the world used to help me. I used to get that data, get that program, paste it here in my code, and the job was done. So it was a collective effort which helped me to develop these many experiments for Pocket Science Lab. Now the next step is where we are trying to give it a good shape, a formal shape, redesign these experiments, redesign the setups so that they can be locally manufactured anywhere if the procedure is given, and try and make this Pocket Science Lab available to all kids all around the world. Thank you so much for your patient listening. If you have any questions, I will be very happy to answer.
All right, if there are no questions, this is the last presentation. I'd like to do a quick wrap up of everything. So give me a few seconds. If you